presenting in the colloquium today. He's an assistant professor in the software technology for learning and teaching group at the department. Research interests of Sergey include various aspects of, he says, designing, developing, and evaluating adaptive educational systems and personalized information systems in general. Sergey has worked in and lived in quite a number of places around the world. So originally from Russia, from Kazan, so he holds his master's degree from there, then went to the US, Pittsburgh, to obtain a PhD in information sciences. And then, he moved back to the European continent, first as a EU Marie Curie fellow at the Research Center for Artificial Intelligence in Saarbrücken, and then also worked there for a couple of more years as a researcher. And what is now something like 5 years ago or so, he joined Utrecht University, and here he is. The floor is yours. Thanks.
Thank you very much. Well, now I understand why I had to send my short bio. Okay, so let me share the slide.
In your case, I even had the information more or less, but it was still handy.
Right. Okay, so let's get started. You can see my slides, right? Okay, yes. Good. Okay. Welcome everyone. So I'm going to talk today about quite a long project that we've been developing together with my PhD student Isaac Alpizar-Chacon. This is why his photo is here. And honestly, while ideas have been generated mutually, most of the work, of course, has been done by Isaac. This is how it usually is. So I will talk about extraction of knowledge models from textbooks, but being a researcher in the field of adaptive educational systems at heart, I kind of came to this topic and to these ideas from the problems that underline adaptive educational systems. And I want to spend maybe a couple of slides to introduce one particular problem that really hindered the development of these systems and the dissemination of these technologies. So the architecture of adaptive educational systems is pretty much set over the years, so the components are known, so there can be some variations, but more or less all these systems, they follow the same principles, same design principles. We have a student who interacts with some instructional content. This content can be some exercises or interactive examples, or can be just tutorial pages or textbook pages. So the student interacts, and then there is also a domain model. The domain model is essentially a composite representation of all the knowledge in the domain in which this particular system works. A composite means that it consists of a set of atomic knowledge components. These components can be concepts, they can be rules, can be topics, skills, but in any case, they are this small piece of knowledge within the domain, and they form together this structure, which is called domain model. There is a user model, or sometimes it's called student model, which is usually an overlay over the domain model. Overlay means that for every knowledge component of the domain model, the system is trying to estimate what is the knowledge level basically the student has for this particular knowledge component. There is also an adaptation model that basically controls how a system tailors its behavior or its content or its interaction towards the individual knowledge levels of this particular student. And there is also this kind of metadata that describes the instructional content. And this is very important because, well, for some systems, metadata can be pretty complex, defining different kind of properties of the instructional content, like difficulty, interactivity, so on and so forth. But what is always there is this link between the instructional content and the domain model, because based on these links, whenever a student interacts with some piece of instructional content, the system can deduce that not only the student has successfully and unsuccessfully answered particular exercise, but the student actually has provided evidence that he knows or doesn't know this particular knowledge component. And this is how the user model is populated. And then all of this basically together completes the adaptation loop, because this user model is used by adaptation model that now can modify, adapt, personalize the interaction between the user and the content that the system has. And once you have this architecture, then you can do some interesting things. So you can, for example, have adaptive feedback, like this system shows in the middle, where as user keeps solving exercises, the system reacts to different steps with different error messages or messages of success. You can have adaptive navigation, where the system presents to the student different cues that help him or her to find their way around the system. It can adaptively generate the structure of the course or of the textbook, so that the structure represents and corresponds to this particular student, reflecting his or her knowledge. And it doesn't mean that all the systems should do all these different technologies, and there are more technologies like this. But in any case, this is basically what the system is trying to do. Now, this particular system is called MassBridge, and it does all these three different technologies. And it can do so because it was built as a collective effort of many researchers who together created a very well-designed database of knowledge components. And not only knowledge components, but also learning objects, this piece of interactive, pieces of educational content. And it is a very large knowledge base, and it has been, as I said, designed through a number of years, and it's very hard to do, right? But if we want to create another system, then we'll have to spend basically the same amount of efforts to do it. Or if we want to modify the system a little bit, we'll have to spend additional amount of efforts to extend it or to modify it in this way or the other. And we essentially currently live in the open corpus world, right? So this is the scale of the problem that we have. So when our students interact with some kind of content online, and there is plenty of content, and the question is it possible to implement this kind of adaptive educational approach within these open corpus settings? Can we automatically discover the good learning objects? Can we automatically link them together and link them to the domain model? Can we then, through these links, interpret the interaction that the student has with these learning objects and populate the student model, and then basically complete the adaptation loop and maintain the interaction between the student and these learning objects? So this is the challenge that basically underlines the research that I'm about to present. So there are some instructional resources on the web that actually can be utilized to try and extract this knowledge automatically. In this particular project, we focus on textbooks, because textbooks are very particular learning resources. They are characterized by focus, so they're created in very narrow cohesive domain. They're characterized by quality because they're usually created by domain experts. They are characterized by purpose. So the purpose of the textbook is to explain knowledge to a novice, essentially, right? And in addition to that, they are well structured. So they're structured into sections, subsections, chapters, and so on and so forth. They are ordered in a proper way, from easy to complex learning material. They're formatted in different ways, and this the format they maintain actually reflects the purpose of the explanation, right? So we have titles of sections and subsections. Sometimes we have definitions that are highlighted, and so on and so forth, right? So formatting is also used as a vehicle to facilitate the explanation of the material from the expert to the novice. And there are of course, some additional structural elements like indices, tables of contents, and so on and so forth. So basically, what we're trying to do is we're trying to use this kind of hidden layer of information that authors injected into the textbooks when created them, and extract this hidden layer of semantics and try to extract some knowledge out of this, right? And through several years, I think have been able to extract more and more, basically, because we can extract topics and subtopics from underlying sections, subsections. We can extract some pedagogical relations, such as prerequisite outcome, just based on the order of learning material and based on the order of these topics and the concepts that the book introduces. We can try to extract types and roles of different pieces of content based on how they are formatted. And we also can extract some meaningful labels and some structure as well from the glossaries that are essentially underlying the indices and tables of contents. And yeah, so like basically that's the premise, right? So if we automatically extract all this information, then essentially we get some kind of knowledge model that represents the knowledge within this textbook. And then we can try to utilize these knowledge models to implement some kind of adaptive services on top of this textbook. We have done several things. So we started with basically developing the approach for extracting the models from PDF textbooks. So we focus on PDF for two reasons. First of all, this is the most common format in which textbooks are freely available online. It's harder to get access to XML-based formats that publishers are using for the internal processing. Plus, PDF is challenging. So we actually wanted to focus on the challenging format because once we can tackle the PDF, then tackling XML is of course less of a problem. Now, this diagram at the end, at the bottom of the slide, is pretty complex. So I don't want you to go through it in details. Instead, I want to go from a phase to a phase basically and present what essentially it does. So we start with basically construction of style libraries. So the textbooks, different fragments of textbooks are formatted in different ways, and these formatting rules, they're pretty consistent across the textbook. Now they can be different between the textbooks, of course, right? So it doesn't mean that if one heading is formatted in this way in one textbook, it will be formatted the same way in another textbook. But within the textbook, they are consistent, and across textbooks, they follow pretty consistent heuristics that can be, extracted basically if you look at textbooks enough. So if we have a page like this, then we can get some information from just how the texts look. So we can see that there are different styles. And some of these styles, they are for titles of chapters. Some of the styles are titles for sections. Some of the styles are just for basic text that present the main content of the book. And then there are also sometimes these particular styles that can present some important information. And then you can try to think what this important information is. And based on the number of styles that we extract, and then based on, let's say, the relative hierarchy of these styles, bigger font, highlighted, bold, and so on and so forth, we can pretty accurately define the roles that content behind these styles actually plays within the textbook. Then the next thing is we process table of contents. So this is also important. And tables of contents, they follow different kind of styles as well. So there are flat tables of contents, hierarchical, and so on and so forth. But once again, if you look at the textbooks enough, then you can actually understand what the rules behind formatting are. So we can also figure out by now already where the pages start, where the chapters, where the subchapters, and so on and so forth. And based on this, we can build this hierarchy of topics essentially for the textbooks and how and where these topics start, on which page, and where they end. Probably the most important part of the textbook for this particular talk is the index, because this is what we've been working with the most by now. So any good textbook has an index at the end, and these indexes, once again, so they can vary in some shapes and forms. Some indices introduce hierarchical items, some indices don't. Some indices use things like see also labels, some don't. But once again, with enough rules, you actually can capture all the variability there is. And we can pretty easily spot where the index section is, automatically, of course. And then we can also identify where the index term is and where the page is when we have multi-line terms, when we have C links between the terms, when we have ranges of pages, and so on and so forth. Basically, all this variability can be captured. And once again, once we have captured this, now not only we have actually the human-controlled glossary of important terms in the domain, we also have the exact places in the book where elements of this glossary, the terms from this glossary, are introduced, not just mentioned, introduced. And by tracing this, we actually can pretty much link where if let's say we want to navigate a student to a place where a certain concept is introduced, this is the precise information that we'll be using. And once we have all this information, then we represent our textbook in a processable format. We are using the TAFE format, which is a well-accepted format for representing textbooks, for representing books essentially. But we also enrich it with some additional information like RDF, because we enrich it with semantic information through the further stages of the approach. Of course, there are some potential problems with these models. We recognize that. So there are problems of subjectivity. So different authors would create different textbooks within the same domain, which means you will have different models generated from it. You would have variability in terms of structure, in terms of labels, how they call different chapters and how they call different index terms even. The focus of the book can be different, the coverage of the book can be different, and so on and so forth. And from this variability in textbooks, you get variability in terms of models, right? So the quality of the models can differ from a model to a model. And of course, if you just simply extract this information from the textbook the way I explained to you, you don't really get a knowledge model. You basically get a textbook model, right? So you get, so there's certain lack of semantics. So it's more structure of the book rather than knowledge that you can get from the book. But with additional processing steps, we can improve on that. Right. So nevertheless, the automatically extracted models of high quality resources, meaning textbooks, and underlying domain knowledge. And if even though individual quality of these models may be not enough, we can do some interesting fix. So for example, we can interlink these the models from different textbooks within the same domain together, or we can interlink them to some external models like a DBpedia or other linked data sets. And once we do that, then we get access to more semantic information, and also we can get access, to a vehicle that is, helps you to objective to have the knowledge more objective, right? Because one textbook is subjective, another textbook is subjective. You link them together. Now you have a more objective view of the domain. And if you link enough textbooks, then basically you can potentially get a very nice model in terms of coverage, in terms of focus, and so on and so forth. So first, we wanted to evaluate whether or not we actually can extract the information from the textbook in the proper way, and indeed we can. So we have compared the so how we compared our approach. We have taken two different versions of the same textbook. For every textbook, two different versions: the PDF version and the EPUB version. And the EPUB version basically is an XML, and parsing XML is a trivial task. So we assume that EPUB represents the correct full content of the textbook. And then we compared what we can get from our PDF extractor. And we compared this against some other instructors that we have found in the literature. And the first kind of orange block here shows that our approach can recognize much better what is the actual text. And why the numbers here is not 100%? Well, the main reason actually is because so we work with domains like statistics, and in statistics you always have tables, you have figures, you have plots, you have formulas, and in EPUB all these different elements are represented as graphics, but in PDF a lot of elements are represented as text, and this is the main source of this mistake. So this is why it's basically 94%, not 100%. Now, in terms of recognizing table of content and index, once again, we are pretty much close to 100% in terms of precision and recall. Yeah, so we are pretty happy with these results. The next thing we wanted to do is, okay, so like once we extract these models, is there any value in them, right? So, okay, we can extract them, but can we actually use them for anything? So we decided to put them to the task, and the task was, if we get two books within the same domain, right, which are supposed to be relevant, can we actually use our models to link sections within these textbooks? So can we, based on the way we create these models, understand that this section within one textbook talks about the same thing as this section within the other textbook? So we have collected two textbooks within statistics. We gave these textbooks to statistics experts who manually linked these sections for us, right? So they provided how strongly sections are related and how certain they are that this is the best possible matching. And after we have done it, we compared our model versus several baselines, and the baselines were TF-IDF, the job frequency, inverse document frequency, and the LDA, right, latency allocation. And so we basically wanted to see whether or not our semantic structure models can bring some additional information to these traditional methods that are being used to represent content within textual resources. And we used the NDCG, which is a usual metric to compare different approaches on information retrieval tasks. And these are the results. So the yellow is our model, and the different other colors are the baselines, TF-IDF, LDA, and then combined TF-IDF, LDA approach. And you can see for NDCG1, which is basically trying to estimate how well your model can find the best possible link, right? So one single best possible link. We pretty much beat all other models, and we beat them significantly. When we go to NDCG3 and NDCG5, so can we find the 3 more relevant and 5 most relevant links from one textbook to another? Then we kind of hit the ceiling effect. And in this case, we do not really beat all the models significantly, but we still outperform the TF-IDF. So even in this case, it's pretty good. But I would say that the second two are less important for us. The finding the best possible link, this is the most important task, and being able to identify it in 70%, 70+% of cases is pretty good. Now the next thing that we have done, okay, so I need to focus on my time. The next thing that we have done is we try to link our models to DBpedia, because like once you link it to DBpedia, you can basically get access to some model that has been already created for you, and you can use it to verify and how well your model represents the content that you have. Once again, don't focus on the diagram. I'll just bring you through the steps. So first of all, we have constructed the glossary. So this particular part was based mostly on the index part, and the index parsing basically helps us to construct the glossary. Then we wanted to recognize what are the proper wordings of terms. So sometimes you have indices which are hierarchical, like distribution, gamma, normal, right? So how do you spell these particular terms? So we can spell them in 2 different ways: gamma distribution or distribution gamma. Same was normal. And then we could, so we have these candidates, and then we go to the actual text of the book, and we extract how these terms are spelled, right? And based on this, most of the time we can identify the correct sequence of words. So it's gamma distribution and normal distribution in this particular case. And then the last thing, so we create the glossary, we represent it, and then we use it for the next phase. So basically what we wanted to do is, once we have this glossary, right? So once we have the proper wordings of all the terms that we can extract from the book, we wanted to query the DBpedia, which is, by the way, the semantic snapshot of Wikipedia, if you don't know. And within DBpedia resources, they essentially correspond to the Wikipedia pages, right? And every resource in DBpedia also has a category, right? So there is a hierarchy of categories that is manually created. In the beginning, what we wanted to do, of course, to limit the amount of information we want to query from DBpedia. So we wanted to focus only on resources which belong to statistics or some relevant categories. So the only manual input that this particular part of the approach requires is that we say, okay, yeah, we want to focus on this category, this parent category, statistics. Then the algorithm looks several levels deeper to extract some additional subcategories which also can be relevant. Then the next step is to create the core set of resources. So once you query a DBpedia, you can, for every basically query, you can get either one or several resources, because resources sometimes are spelled the same. The terms are spelled the same way, right? So you can query, you can have a query like mean, and then one of these resources that you would get would be statistical mean, but then there will be a bunch of other things which are related to mean. And this happens for most of the queries, but sometimes you actually can hit a query which retrieves only one particular resource. And if we get a query that receives one particular resource, and every query for us is the term from an index, and we see that this resource corresponds to one of the relevant categories for us, which is either statistics or some of its subcategories, then this becomes a part of the core set. So we know that this is a resource. That's the DBpedia resource that represents a term from statistics. and then we can add it to the core set, and we get also the abstract of this resource, because the Wikipedia stores the abstracts extract from Wikipedia, and we kind of concatenate all these abstracts to create the context, the word-based context, basically, the term-based context of the statistical domain. And we use it on one of the next steps. So if a query retrieves several Wikipedia resources, right, like in this particular case, so they can form a candidate set for this particular term. And then we get the context for each of these candidates, which is basically the abstract of this particular candidate. And then we compute the cosine similarity between its abstract and all the abstracts of the terms for which we already have found resources, right? And if cosine similarity, whichever resource has the highest cosine similarity for this particular term wins, and if it's above the threshold, then we see that it is also basically a term that corresponds to statistics. And we add it to our core set, and we extend the core set context with the abstract of this resource. So basically, we gradually verify from the smaller set to bigger and bigger and bigger set, which of the terms, which of the Wikipedia resources correspond to which terms within our textbook index. Right, and once we have this, so we also can enrich our model. So now we have a little bit more semantics within it. So we can get the abstract that the Wikipedia provides. We can get the link to Wikipedia page. We can get to which category it corresponds, to which subcategories, relation to other terms, and so on and so forth. Right. So now actually we have a much better, we have a model that has much more rights to be called, a knowledge model, basically. So all these things now are available for us. And we extend our TAE model with additional RDF-based attributes. Now, of course, we wanted to evaluate whether or not this actually works. And what we did essentially is we have created a we have created the ground truth manually. We have linked the index terms from our books to the Wikipedia resources manually, and then we compare. We wanted to compare whether or not our approach actually can find these resources on its own or not. And we compare it against two baselines, but these baselines are, just these standard baselines that people often use in these kind of tasks. One is random, and one is the most popular resource in the candidate list is selected. And the plot you can see. So these are the plots for 3 different books. Yes, 2 statistics books and 1 information retrieval book. And these plots show how the precision recall varies depending on what is the cutoff threshold, basically, when we compare whether or not a resource actually belongs to statistics or not. And you can see that for all the different textbooks, somewhere around 0.6, 0.4, this is where our precision is still pretty high, and this is where recall also, is getting very high, right? So, and we see that the numbers are actually pretty well as well. So it's around 0.8, 0.9. Well, for information retrieval, 0.7. Another thing we wanted to check is what will happen if we integrate multiple textbooks. And we did this. So we tried to we queried Wikipedia based on one single textbook and how many resources we can retrieve successfully based on one single textbook, and then based on 3, and then based on 10. Based on 5, and then based on 10. And essentially, once again, so these plots show the differences, right? So for a single textbook, the precision, is pretty high, but the recall is pretty low, right? Because, well, single textbook does not provide you with enough information, I would say, compared to the set of statistical resources that you might retrieve from Wikipedia. But as we increase the number of textbooks, the precision remains pretty much the same, but the recall, really grows. And if you compare the 1 versus 5 versus 10, you see that, we basically get from only 10% of resources recalled to, well, 35, 40. Probably if we keep extending this, we will get even higher. And by the way, in this particular case, the target set of resources, manually created resources, was done based on this ISI glossary, which is the biggest curated glossary of statistical terms in the world, and it's curated by International Statistical Institute, which is basically the standard station organization in statistics. So I'm pretty sure that whatever resource is in this glossary is a statistical resource. Okay, so I'm almost done, and I think I should be pretty much almost done. So the one thing that I want to present last is what we're working on currently. And if you are interested in this particular part of our work, then I welcome you to visit Isaac's poster that he will present during the department poster day, which will happen soon in May. So if you look at the terms that you extract from textbook indices, you will notice that not all the terms, of course, correspond to the domain of the textbook. So there are some important terms, some core terms, like if we talk about statistics, there will be terms like standard deviation or mean or median or regression, analysis of variance, and so on and so forth. Then there are some other terms which are maybe less important, which correspond to more niche aspects of the domain. So, for example, scatter plot, right? So it's a statistical term, but it's not that it is the most important term in statistics. There are also some terms which are kind of related. So they might belong to other branches of mathematics, and they can be used sometimes in statistics, to explain certain statistical inferences or certain concepts, but they're definitely not the core statistic terms. And plus, there are also often terms which just do not belong to statistics at all, and authors use these terms for pedagogical reasons, to exemplify something, to show some anecdotal evidence, to explain some use cases, and so on and so forth. But they still are parts of indices. And of course, if you want to extract a proper domain model of statistics from a statistics textbook, you kind of want to filter, at least these two other categories out, and maybe to weight differently the core domain terms and the in-domain terms, because in this case you can have a much more targeted adaptation. Let's say if you want to then implement something like this based on this model. And this is what Isaac is doing right now, actually. So he is automatically, once again, extracting these different roles of concepts from DVpedia. And he's currently computing the data, but so far the evidence is pretty promising. So I think during this poster presentation, he will show you some interesting results. And yeah, this is it. This is my conclusion. I am not going to read it, but if you want to use to collaborate with us, so we actually have all our code free available online, and also have our service freely available online. So if you want to try process your own textbook, the PDF textbook, so you can actually upload it and then retrieve the model that we can extract from it. Thank you very much.
Thanks, Sergey. So usually we have like a virtual round of applause at this point. So if people want to unmute and join in the thing or post something in the chat, that's fine. Yeah, it works. All right, I'm just checking. There's a question in the chat from Alexander. Do you want to unmute and ask it directly? Otherwise, I can read it for you.
If you can hear me.
Yeah, we can.
So yeah, your example seems to be on a textbook that's from the exact sciences and from higher education.
Right.
Have you also tried things like primary education or topics on philosophy, social sciences, things that are not as clear cut, in my opinion?
Right. Yeah, definitely. And this is a very good question. This is something to explore, because depending on the domain, of course, you can have very different quality of models, and in some domains it probably will not be even possible. So, there are very new domains where the knowledge has not, the consensus has not been reached yet, or there are some domains which are very contradictory, like history, for example, right? So you read different books about history, you have very different viewpoints, and maybe it will not be possible to extract anything there. So we have looked at different domains. We have looked at classical philosophy, we have looked at statistics, we have looked at information retrieval, we have looked at, I think, at some social science domains as well, but we didn't go beyond university domains, no. One of the reasons is because, yes, indeed, we just, for now, we have not really had time to explore the relation between the quality of the domain or the characteristics of the domain and the quality of the models that we want to extract. This will probably take another PhD. And another thing is that essentially currently we are trying to work towards a system that will be able to adapt based on these models, right? This is the ultimate goal for us right now. And in this particular case, we want to support, let's say, self-regulated learning by a student, right? So we want to help a student, who is, okay, so he has found a textbook, now he wants to study it. So this kind of mode of learning is usually for, suitable for university level students, not for children in a school, right? For whom much more benefit from more structured way of education, right? So I would say this approach might not work that well for them, but I mean, so never say never. So we haven't tried it yet. So maybe at some point we will go there as well.
Are there other questions? Please raise your hand if you want to ask something, or put it in the chat. I was wondering, Sergey, also when you were saying so people can use your service and upload their own textbook and so, but how was it with the legal intellectual property side?
Right.
I mean, I could imagine the metadata as such as this stuff is in the textbook. I mean, that's probably metadata that's not so crucial, but how deep do you go into the content, the protected property, and are you allowed to do? Is that something to consider? I mean, I was also thinking it could be an interesting business model maybe for textbook publishers, right? I mean, you do have this model and you sell the content, not the whole book, but like piecewise.
We're thinking about it ourselves. Yes. By the way, if anybody has access to good publishers, please hook us in. So yeah, about the legal aspect of it. So first of all, we take all our books either.
Sorry to interrupt. Just Alexander's suggesting that you stop sharing. Maybe.
Oh, I'm still sharing. Sorry. Yeah. Okay. I should stop that. Yes. Thank you.
Thanks.
So we take all our books either from open database online, and there are quite a few, or from our library, and we discuss with our library which publishers actually would give their consent to use their textbooks like this. And so far, we do not present these textbooks to anybody, right? We just extract models. And even once we extract models, let's say, and give access to students to these textbooks are already available for our students. So we are not actually violating any. So as long as only University of Utrecht students get access to whatever products we get, it's not a problem. And we have, I think, two publishers. Isaac can correct me if I'm wrong. So Wiley and Springer are the two publishers that have agreed that this is okay. Now, if somebody uploads to our service an illegal textbook, he will receive an illegal domain, an illegal model, basically from this book. I mean, so we cannot stop people from this, from doing this. But I once again, we do not distribute, we do not reuse, especially commercially so far, all of this. So the only thing that we do, we basically extract the knowledge model out of this book and then make it available, right? And in this particular case, I don't think we violate anything, even for textbooks obtained in illegal manner. You know that there are quite a few of them online.
Yeah, it's really not hard to find the major textbooks somewhere.
Yes.
Yeah. I'm good. Other questions? Someone? Yeah, Alexander had another comment, I think primary education might even have more online learning than higher education by now.
But it's a very different online learning. So they learn basically. So they just replicate the regular classrooms in online, right? So they have their own systems. They have exercise services. They use Zoom to conduct lessons. It's very different. So they're much less autonomous than a university student might be.
I would concur actually, but it depends also on the school type. Montessori onderwijs, for example, is a lot more independent. I feel that the current primary education sometimes is more independent learning than I had at university. But of course, it differs. But I have one other question. Are you also collaborating with the Freudenthal Institute?
Not yet. No, not on this project. So
that would feel like a no-brainer for me.
we know good people from Italy. Well, so let me put it this way. So currently we have not really moved to education part of it, right? So we are really focusing on domain representation. We are focusing on extracting knowledge from textbook and making sure the approach actually is plausible, right? So that we can actually get something which is accurate enough and usable enough that later on you can build some services on top of. And this is what icsc is about. But I hope to get more students in the future, and maybe at some point we will get to the interesting stuff as well. So actually generating adaptive textbooks in one click, or maybe to build in, a huge global knowledge graphs based on textbook, because this is another potential application, right? So imagine integrating all the textbooks that have been ever written, extracting knowledge models from them, and then building them all together. That can be interesting too. So if anybody is interested in this or have any other ideas, please get in touch with me. We can work together.
Yeah, maybe one thought I was thinking that, I mean, if it's not the high school students or primary school students directly using the services, it could be still their teachers, right? And like compiling new material for the classes. I mean, in that sense.
That's true. And we actually talked with one publisher, for example, so which is along the same line. And one thing, for example, that publishers are currently trying to do is they're trying to move from the business model of selling textbooks to business model of giving access to intelligent services based on top of textbooks that they have created, right? So they're selling licenses to their textbooks online, plus some additional services are built on top of these textbooks. And to build these services, they do need models like this. So we have talked with this publisher, that yes, that would be great if we could, generate a domain model for you, and you can implement adaptive exercise, for example, based on this domain model. But unfortunately, it didn't go very far. So they were busy, too busy for us, and yeah, at some point, I think the connection has broken. But maybe next time. Maybe next time.
Maybe in the future. Yeah.
Maybe.
Cool. Are there any other questions? If not, then you deserve another round of virtual applause from all.
Thank you very much.
I don't know if anyone's joining. Yeah, but I think that's closing the session for today. Or is it another hand, Alexander?
Oh no, wrong button.
Another question.
No,
Okay.
I think those were the virtual applauses.
That's fine. Yeah. I think that is one of the features that Zoom has. They have more symbols for these kind of things. No, but I think with that we will then. Yeah, thank you again for this interesting talk and for answering the questions. And yeah, we'll be back again next week for another colloquium. Enjoy the rest of the day, folks. See you again.
Bye bye.
Bye bye.